Bonn, Germany, and another from University of Southern Denmark. He had research interest in the area of quantum optics, quantum sensing, quantum information and processing, quantum simulation. So today we have requested him to have his lecture on this basic mechanism of quantum sensing and to discuss about this atomic state-based sensing. So once again, I welcome you, Dr. Noman, and I request you please start your lecture.
I thank you, Kamlesh, for nice introduction and going through all my past records and introducing it to everyone. So thanks a lot. All right, so I will start with the talk. And so based on the kind of interest in general in recent time about things related to quantum, so other than quantum computing and so on, quantum sensing is one of the fields that has already grown in the past, and we are already using a lot of applications on that. And in the recent time, with the advancement of various other technologies, the field is kind of growing a lot more faster. So I'll start with my talk with the outline here. So it's the first thing I'm going to introduce a little bit about classical sensing, and I'll give some examples. So there are, of course, a lot many, but I'll just walk through some basic examples and show you what the limitations are with the classical sensing technology. And then why do we need to change the sensing technology towards the quantum? It comes to this bullet point here that's related to universal standard of measurements. So I'll cover that as well. And then the next part, which is the main part of the topic, is the principle of quantum sensing. So that I'll just go through the basics and build from there. And then some of the examples are like the later parts that I've left for the next lecture. So I'll mention those as well. There'll be some examples in this talk, and then I'll summarize this is my talk. All right, so this is the so by sensing, we already use a lot of different types of tools in day-to-day life. So, for example, a spring balance that we can use to kind of measure the weight of some object. Similarly, a pendulum that gives us a count of time, and then thermistor, just to give another example, we use to measure temperature. And one of the things that all of these or many other sensors they do is they respond to a given physical property change. For example, if you add more weight, the spring length would kind of extend. Similarly, high temperature, the resistivity of the sensor will change. The pendulum, if there's like a different gravity, the period will change, but I think that's not the main point. The idea is that it kind of measures time. Okay. Other thing that's very common in all of these and pretty much all the other classical sensors are all these behaviors that we measure. They depend on the collective behavior of large number of particles, meaning each of these components they're made out of atoms and different molecules and whatnot. And here, as a whole, a bulk behavior is what we measure. So just to illustrate, so here's a part of the spring that is used in the spring balance. And this is like the parts that I'm showing here is the atoms that are kind of vibrating in random direction. Although the spring moves in one way or the other, but the inner parts are all moving randomly. That creates sort of like a vibration on a macroscopic level. And then similarly, in the pendulum case, the string also has different atoms and molecules. They are stretching and compressing against each other. Uh, in the case of thermistor, we do have electrons moving randomly here and there. That's a classical picture, but that serves the purpose in this case. So overall, there are a lot of random motion and movements that are going around. And what we are measuring is the average effect of those. So one could think that maybe those random motions are not going to affect because they would just average out to zero. But that's actually not true in real scenario. Just to show what I mean, here's an example of two particles separated and bound with like this string. This is just to illustrate the bond between two nucleus or two atoms, and then they're kind of doing a harmonic type of motion. But in reality, so one would expect it to have like this green curve that shows the harmonic type of oscillator. In that case, the mean value would point to the center value here. But in reality, they have an harmonicity. And that's easy to understand because it's kind of, you can think of, you cannot compress it too close, whereas you can stretch it further away. Therefore, the curve here shown in the blue, that anharmonic type of potential, is what sort of illustrates a physical, a real picture of a mechanical system. So the summary of this slide is that it's the measurements are first noisy just because of the lot of randomness, and we cannot address individual particles or constituent atoms or electrons or their motion. So that gives you a lot of randomness. But then due to this anharmonic potential, there is systematic drift in the measurement. So like those pendulums, that what shows time, it changes in like due to temperature. Winter or summer, it would be quite different time. So similarly, all these mass spring balance of these thermistor-based systems, they're not going to function properly and linearly over a full range. And again, like if you repeat this whole measurements here versus somewhere else, those values are not going to be consistent. So one clear outcome from those tests, they're not fit for a universal standard of measurements, which had been there for past, some kind of different types of imperial or other kind of measurement system that were used. So now just coming to what these universal standards are. Before I move, by the way, like if there are any questions, please drop in the comment. I'm fine with that. So I can see the message here and respond accordingly. Okay, so back to the topic. So here is the SI system for units. So this is important because all our measurements that we do here or anywhere on Earth or probably elsewhere in outer space or wherever, they need to be agreeing with each other. And just before, please explain limitation parts once again. Okay. Okay, so limitation, I see. So the part here, so what I'm describing here is that the classical sensing technology generally depends on the kind of a bulk behavior of the whole system. And these behaviors are kind of, they are not very linear, and mainly also because there is anharmonicity, meaning it's not a harmonic type of potential. So you can see that this blue curve, meaning if you increase the temperature, the average distance between the two particles would be further away. So that would depend on the temperature. It would not remain fixed. And therefore, this is like one of the major limitations. And I mean, there are other limitations as well, but this is like just one major part that kind of sets this kind of part. I hope I answered the question. So you can message anytime. Okay, so in the year 2019, there was a kind of it's a big news for the entire scientific community that they changed the definition of some of the uh, kind of units. Personally, I had hard problem during my like the school times about ampere being one of those units and not current. So they kind of now redefined it, and charge is the fundamental unit which defines an unit. So just going through some of the parts here. So the second, which had been defined and it was changed in like 1980s or something. It was defined to hyperfine transition of cesium atoms, and so that remained the same. On the other side, things that change is one of these things here is the IPA, so it's an international protocol for kilogram. It's a block of iridium, sort of platinum iridium alloy, which is sitting somewhere in Paris. And they use this as a measure of 1 kilogram. So in the entire world, people like India and everywhere else, they had another similar IPK calibrated, the one in the Paris. And then like all your measurements are kind of calibrated from there. Those calibrations are kind of prone to change because this is not standard. Like measurement of kilogram depends a lot on the how you measure them and so on. And so this is not a standard unit. It's somebody just named it and gave as a 1 kilogram, not good enough. The other unit was ampere that was based on force between two wires separated by 1 meter. So this involved a lot of different problems. So you need to measure the force, you need to measure the distance. So there's like a lot of different dependencies, and that led to kind of problem in defining this unit. So the newer unit, it all converted to more like a constant. So everything around here, a constants, speed of light, charge, kV, candela, and then I forgot to remember Planck's constant. And then the second that stays defined as the hyperfine line of atom. So that's where it becomes very important to kind of start looking into quantum systems, because that's how you can probe and detect and measure those transitions. So with the help of just this definition, most of the other units can be redefined. Okay, so the time is like the main kind of component for the definition of all the units, and therefore in the next slides I'm going to focus a bit on time. So here is like now is the world of quantum system. So this is like a picture of cesium atoms with very classical hand wavy picture with a bunch of electrons. But important part is there is one electron sitting in the outside that makes it pretty much like a hydrogen type of atom. And so it has very fine and clearly defined transition lines. Other components or other elements also have that, but for certain reason, also for application-based system, cesium turned out to be very practical. So in one of these hyperfine transitions of cesium ground state, they're labeled as 3 to 4. I'll show you these things in the next lecture in the details. So these the transition between these states correspond to a frequency that's 9.192 gigahertz, all counting all these numbers. So this is actually now the definition. So it's 1 second equal to these many oscillations of this transition. So you make a device, you count those number of oscillations. Once you reach this, that's 1 second. So that's the definition of time. And this definition and like synchronizing everything with cesium has been very useful, and we have been using it since ever. Just walking through some of the examples. So for example, these GPS satellites system. So it's so they launched long ago a lot of cesium clocks in satellites, and there are about like 31 or 32 satellites that are available to common public for navigation and location. So your mobile phone that detects the signal from the GPS satellites, and based on their arrival time, they estimate the distance of each of those satellites, and then you can the phone runs some mathematics down there, and then based on their distances and arrival time, you can estimate the location. So that does not need any introductions. That's like real practical application. The other thing that these satellites can do with the GPS on it is a synchronized clock between two different parts of the world. So you can send signal here and here and synchronize all the clocks on the ground. And that way, the clock between two different countries are in sync with each other. And this synchronization is very important for, again, another set of examples. For example, here, this is case of a power grid line. So power grid is a very complicated system with source, and then lots of powerhouses supplying power to the grid system, and they're all distributed wide range of places. And one of the things that they need to manage, because those power lines are 50 hertz, so they need to make sure that each of those power supplies in the distribution unit, they are in sync with each other. So one way to know their phase is by measuring with some sort of reference signal. So suppose a signal here and then another signal at another station at about like a couple of 100 kilometers. The reference signal it would be hard to manage the reference signal, but those are all possible today with GPS synchronization. So then you can use those and kind of synchronize your phase just by knowing the delta and adjust accordingly based on how the system develops. Another practical example is in the world of the stock market. So there's this thing called high frequency trading, where the trades are happening at very, very fast rate, because there are big companies and investors involved who are buying and selling randomly at different times. So consider like millions of buyers and sellers. This sell stock, buy stock, and then the actual fluctuation of the market value could be very fast. So this example, on a 1 minute time scale, you barely see any difference. It seems like the two index points are pretty much at the same time. But if you zoom in and look into a faster time scale, there seems like there is a difference between these two stocks. And for example, at this stage, we'll sell this stock, buy this stock, sell this stock, buy that stock, and so on. You can make decisions. Although this is very fast time scale, you don't do those decisions. It's the some hardware based on FPGA and other kind of AC world, you can use those. But this is the kind of this requires the time synchronization, which again you need to get it from standardized time, and GPS based clocks are kind of linked to the atomic clock. Okay, so now there's a question. So why do these measurements, like showed in this in the classical system, there are like problems due to uh, inharmonicity and those kind of stuff? Why do those things not? Why are they not present in vapor cell based system? So first of all, the most important part of all is individual atoms. They have identical properties universally. So one atom of any atom you take, cesium or hydrogen, here or moon or on a star or anywhere in the or universe, they have exactly identical properties. And that's been used for detecting and sensing stars and their life and so many different types of stuff. So this is most important part. Okay. The other thing is you can protect these atoms in some kind of enclosure. So usually there are vapor cell. So it's basically made out of glass with a bit of vacuum in it. So no other environmental particles. So no air or anything is in there, except for the atoms that you want. So you can fill cesium in there. So cesium comes as like a chunk of metal. It has a very low melting point, about like 28 degrees. So it stays in vapor and solid phase. That like you just put a little amount of cesium in such glass enclosure, it would uh, release enough vapor for us to do these testings. The other thing is because of low vapor pressure, their interatomic distances, and also they're not in solid phase, the interatomic distances are much larger. Therefore, the problem that we were seeing in the classical sensors like metal or any solid state object, uh, the atoms are very close, but in this case, um, they are very far apart. So you can treat them as individual atoms, and also the results show the same. There are then a bunch of different measurement techniques that have been evolving. So uh, this picture I'm showing is based on a vapor cell setup, which is at room temperature. So you just take a vapor cell and you don't need to cool down or anything, or you don't need to make it in very special environment. Here, what other options you can use is there's a technique of called laser cooling. So you can use a bunch of different types of lasers and in a different geometry, cool down atoms to temperatures close to absolute zero. So it can never reach absolute zero, but it's close, and it's about hundreds of nanokelvin, just above zero. That's quite remarkable. And at that temperatures, you start to explore a lot of different types of behaviors. So system. So that's actually very useful. And but those are very complicated systems. You need to build a whole lot of lab and a lot of different system electronics, different vacuum components, and so on. It's hard for any sort of field testing. In this talk, the first one as well as in the later talk, I'm going to just present things that are more for real world and practical uses. So the vapor cell type of system is very useful. All right, so now coming back to the main part of the topic, that's the quantum sensing. I think just stop. So I think I'm going to take a little longer, but I'll cover up that in the next talks. It will be a balance of two because I'm also building the base for the next one. Anyway, so for the quantum sensing, there are a set of criteria. So first thing has to be discrete and resolvable energy level. So the system that we are going to use for sensing um, anything with quantum has to have a set of discrete states, which is one of the kind of results in quantum systems. The states can be initialized and in a controlled manner so that you know what state you are in. And I'll walk through each of these points in the coming slides. And then there is a term called coherent manipulation. So coherence is a very generic term and it is used in various different uh, fields. And it's kind of sometimes it's confusing, but coherent means something that has a good phase relationship. So in this case, like quantum systems do have certain kind of phase. When you manipulate them, you're at risk. Let's see, there is a question. What's the question of inter-atomic distance? Some classical system. Okay, so the question is, what's the implication of interatomic distance, more or less on classical system as well as mentioned in atoms in vapor phase? Well, so the implication of the interatomic distance is that once the atoms are getting closer to each other, they're going to have some sort of interaction on one another. So the field from one atom is going to perturb the other atom. Therefore, their original or the fundamental transition lines are not going to be the same. Therefore, it would be hard to treat them as a individual atom. So that's why we use low density and kind of dilute vapor system so that they're far apart and they're isolated and can be treated as single individual. Okay, back to the topic here. So the interaction with physical quantity. So one of the other criteria for the quantum-based sensors is that they need to have interaction with physical quantity. So, for example, any kind of field, radio frequency or electric field, magnetic field. And just answering to the previous question, it can also sense the presence of other atom around, and that is going to be kind of not in a good way. So indeed, the atoms do have a lot of physical, like interaction with physical quantities. Okay, so I'm going to walk through each of those points with showing some examples. So the example I'm going to show is with cesium atoms, and for no other reason than just it's very simple, although it looks complicated, but it's one of the most simple system when you're dealing with quantum systems here. So in cesium atom, you have different transition levels, so 6s, 6p. Then these states can be resolved further in these labeled by 6s p to 3.5 and even half, and they can be addressed by certain lasers, and they are labeled here 852 and 894 nanometers. So these are discrete states, but then can find that these states are also not single and individual. There are more finer states, and they're called hyperfine structures. So these hyperfine structures are what we're going to use for this talk, and also that's what we generally use for many experiments. So in the hyperfine structures, it comes from the interaction of the total angular momentum with the nuclear spins of an atom. So that splits the line into multiple. Each of the lines are split into two, and depending upon what their spin number is, in this case, it's 4 number of lines. And their splittings are on the order of tens of megahertz or even gigahertz. And just to give you kind of the perspective, uh, the frequency of Y cesium, it's one of the reasons because it has a good vapor pressure at a room temperature. Therefore, it's easy to manipulate and address these atoms with laser, and you don't need to make very complicated system. So it's just a convenient choice. But also the energy lines are very clear. Anyway, so back to the question, back to the topic. So here, these lines, just to give you the perspective that these numbers, like 100 megahertz, 150 megahertz, they are easily tunable by the present day laser technology. The lasers that we work on, they are much better than like 1 megahertz. They can be even narrower, so it's easy to tune for each of those. So that answers the other question, that initialization in the well-known state. So to initialize in to any state, you have atoms depicted by these black dots. If the atoms are in F equal 3 hyperfine state, you can use a laser that's need to kind of tune the laser. So there are different techniques. Some parts I'll cover in the next talk. So the atom can be addressed and excited to different citation levels. So for example, just by using 84094 nanometer laser, which is exactly tuned to this transition, would pump the atoms here. Similarly, those atoms can be pumped to a different hyperfine level here. So that's addressable. Then the next part we cover is the superposition of the coherent manipulation. So one so the coherent part where what I discussed is have to have a good phase relationship. So for example, if you have some atoms in this state and some atoms in this state. Now, this is one example in which you use two laser system. I'll discuss that in the next talk as well, but just bear with me. So it's the idea is that if you use two lasers, that forms some kind of path from here to here via this other some state. Atoms are like excited here, but then brought back by this other laser to this state. So there is it barely stays here. So you're kind of transferring atoms from here to here as well as here to here. And there are certain types of protocols in which you can change the power of the lasers or the detuning of the lasers and control it in such a way that the atoms can form a superposition state shown here by blue. So it says like it's blue and brown dots on top of each other, which basically means that the atoms now are in a superposition state, which means they're both at the same time in 3 and 4. They're not either or, but they're both. That's what the quantum superposition means. And they have a sort of some phase to it. So I'm not going to do any kind of mathematical type of expression, as those are generally covered in books. So I'm just giving you a more like broader picture to kind of get some idea and use it as like more like a real world kind of applications. This plot shows that based on these controls, the population from the blue state, which is the lower level, can go down, and then this can go up. So you have sort of like different, you can reverse the process as well. So you can create any sort of superposition state by just controlling the lasers. So this is a tool well developed. It's is used in labs every day. So it's that's one way. Okay. The next criteria is um, interaction with physical quantity. So again, looking at this transitional state, because this is also the clock transition that we use in atomic clock. I mean, there are other atoms and other species that are used, and they are even better. But this is like historically built, but also very robust uh, for like working in any environmental condition, such as they are remotely operational in satellites for ages, in like decades. So these kind of clock states are actually very good and easy to work with. So just to give you example, like if you have a frequency, a radio frequency corresponding to 9.192 blah blah gigahertz, that would address these two states. So if you have this radio frequency on, it would start to populate the atom, or like swap the population of the atom from ground state to the upper state and back. So that's the population change. This is just one example. You can do various different types of tricks. You can send pulses of radio frequency and change in between and so on. But if the RF is continuously on, the population goes up. This is called like Rabi oscillation. It's very common and very well known term in quantum physics. So this is also this step is also used in many of these quantum computation business, where they talk about the qubit, and then you need to create some special state. You can light pulses. Okay. Now, after showing those criteria, those were the fundamental criteria that the system uh, kind of is characterized as a quantum sensor. So this slide showing a very basic layout and very basic system of how a quantum sensing process works. You start with a initialization phase. You have mainly these two-level system, but as we already saw, there are more levels, so you can actually leverage from those. So to initialize, you use a laser, and this from state 1 to state 3. And then from this state, atoms can decay naturally because of certain their low lifetime. So they would come to this state as well as to this state. But because this laser is continuously on, it's kind of like pumping. So it'll pump all the atoms to this state. So after some time, usually it's on the order of tens of microseconds, all your atoms would be in this state. So normally these two states would be populated, but you can just populate one of the states. So this would form like a pure system of all the atoms in one state. Now it goes to the next part, where the exposure, the field. So you're going to detect radio frequency or electric field or magnetic field or any kind of field, like even gravitational field. This is the exposure phase, where you leave the system to the field, and the field would kind of evolve the system in certain way. And after that exposure, you can detect it. So it's a readout process. So in this case, you can shine another laser addressed to a different transition state that I'm showing here. This state does not have any decay to this level. This is important because then you don't want to change the population. You're not doing the pumping, it's the opposite, it's detection. You just want to know how many atoms are there. So in that phase, you just drive this, and the laser, you look at the absorption signal. So when you send the laser beam, look at the signal, it will show if there are more atoms. So if there are lots of atoms in the ground state, that would show more absorption. So you can quantify that there are lots of atoms in the ground state. Or if there are no absorption, which means there are no atoms in the ground state. So by that information, you can find out how many atoms are there in the ground state and in the upper state. And this population distribution is generally used for estimation of what the field has done to the system. So that's like general overall overview of the whole process. I'll give you some examples in also in the next slide, the next talk that shows some another set of real world applications. So, okay, now coming to the types of sensor based on quantum technology. So there are, broadly speaking, like three types of quantum sensors. So one is energy level based sensing, in which you kind of look at the energy level of because those energy levels are discrete. So you can try to measure those energy levels and see whether that changes or not. So any change in that energy level is like one method of estimating the given field. The other types of sensing is based on coherence detection. So the coherence is mainly due to the interaction and that causes interference between two states, and that creates the superposition state. And then once the superposition state is created, it can evolve in certain way, and you can detect the phase of that. So these are useful for detection of like gravitational field and so on. Then the third type of application, which is like quantum entanglement based, it's actually a very complicated topic, and I've tried to cover that in most easy language, but let's see how that goes. But this is there are terms like spin squeezing and non-demolition measurements, and these are kind of hard to grasp the picture of, but I'll discuss that. Uh, One of the important things about this entanglement measurements are this is in some sense the true quantum sensing, because in all these other cases, the somewhere or the other, like atoms are quantum object, but what we detect it with a laser beam is not, it can be made a quantum, but it's not in quantum state when we detect. But in this case, all of those are in quantum state. So the light and the atoms. So it's kind of a more complicated business, but it has a clear advantage, says the Heisenberg limited measurement. So in normal sense, the limits are kind of what it's called as photon shot noise limit. So it's a I'll discuss that in the slide. So let's go through these first 2 points first. So quantized energy level system based sensing. In this case, so you have a two-level system here, and you apply some kind of field, it can be radio frequency, magnetic, or anything, and that changes the energy level. So it moves the energy up, moves the energy down. You can use a laser and just look around here. If you scan the laser, you will see a peak. So that shows usual spectroscopic technique that shows a peak. And then if you scan a laser, once there is a field, you'll see the peak is shifted. So the shift is a measure of the given field. You can use this technique to estimate what sort of field is there, and you can calculate those amount of shift from using some quantum mechanical principles. So then at the end, everything will boil down to the atomic properties and a bunch of constants. Those constants are, well, constants, and everything is linked with atomic properties. So these measurements are going to be SI traceable, meaning you perform this measurement here or anywhere else, they are the same. You don't need to calibrate in any device or anything. So just perform the measurement. So that's an example of sensing based on energy level. The coherence, quantum coherence-based test sensing, it's another example. Looks a little complicated, but it's actually not so much. So you all are familiar with light interferometer. So it's a beam that comes here. It splits into two. So think of this as a beam splitter. The beam comes here. It splits at two parts. There are mirrors that flip them, and then they come back to another 50-50 beam splitter, interfere, and then they go in two different parts. Atoms, they also behave like wave, just like light behave like particle. So that's what the coherence property of these atoms are. So when you have atoms, you prepare the atom in one of the states, you can use a certain laser that would work like a beam splitter. These are technical things, but you don't need to know right away. But what it does is kind of changes the population into 50-50, so midway, and then one part evolves up, one goes the other path. It takes two different paths, exactly like the optical interferometer with lasers. And upon covering this entire path, you have two different paths. And then if there is a phase difference due to it has taken two different paths, then that would show up as interference, meaning the population when you measure here and here would be different. That depends on the phase that it has accumulated. Exactly the same way as optical interferometers. So the advantage here is one of the things that goes on to is the de Broglie wavelength. So that's h over p. P is the momentum. The momentum of these atoms you can control. You can change to fast or very slow or whatever kind. So you have very different types of wavelength. So that's one kind of characterization. The whole system is well, it's a matter wave interferometer. In the case of light, because light does not interact with many things like gravitation, for example, so light won't detect gravitation directly, but atoms do. So you can make such kind of interferometer, and you can detect a gravitational field. So you can make a gravitational field map around Earth or any place. You can use two or three multiple such interferometer at a certain distance. You can measure the gradient of gravitation. This is another like hot topic of detecting what's inside Earth. So if suppose there is like a very dense and different types of like there is a mine or something down underneath that may have a different gravitational field. So that can show if you map with this kind of a gravitation wave detector system, you can be able to detect some like influence of that. Okay, there is a question. So do we have any sensing devices or quantum hardware for classical sensing replacement? Yeah, I mean, atomic clock is very simple sensing device that we use for uh, all the classical device hardware, and there are numerous many. And some of the examples I'll show in the next lecture as well. But also, what I'm showing here, they're already built and tested. For although this is like very complicated system because we're talking about atoms and they are in a very special phase in like cold atoms or BEC. That's called Bose-Einstein condensate. So yeah, they're there on the hardware, but there are generally certainly very difficult to make. So it's not that easy to build all many of these quantum sensors. Okay, moving on to the next part of the talks. That's quantum entangled based weak sensing. So it's one example is based on a weak measurement. So Remember the interferometer experiment in which you want to know the population in a given state. You can use a laser and directly measure the population here. But if you use a laser, the quantum system would collapse. So this is called like collapse of state. There would no longer be a quantum system anymore. Once you use a laser and you detected it, it's gone. All like you can detect and then it's gone. It disappears. It's not a quantum system anymore. You have to restart the whole initialization process and on the testing. So that's how uh, this type of measurements works. In certain experiments where we actually don't care about these collapse because we just measure and that's it, and then next set of atom would come and restart the whole process again. But this has certain advantage, but not like complete. The other way of doing it is you can do a little what is called as weak detection. The laser is not exactly on the transition, but slightly off. In that case, your atoms are not going to collapse completely, but you would still get some impact on the light, and you can detect that. And there are different again techniques to do so. And there's something called like dispersive detection, in which the effect of the atoms on light would be like it would shift the phase of the light and not be absorbed. If it does, the atoms are not absorbing light, in that case, it's not going to collapse completely. So they still remain in the same superposition state. So you can read it again and again. So you can do repeated measurement. That would improve the signal a lot. So that's another one type of quantum entanglement sensing. The next part is spin squeezing. It's it's a it's a kind of a nonlinear process. So it doesn't have to have an atom. So first part here is an elliptical polarization can be represented as a circular of opposite types with their different balances in power or strength. So if you send an elliptical beam into a crystal, or again, can also be a vapor cell, when atoms do serve very good kind of system for spin squeezing. So you have a vapor cell filled with atoms, you send a circular elliptical beam, and then after that it goes through, after it undergoes through this, it would be further rotated. And this part is a little hard, but it's because it has a some kind of process called polarization self-rotation. You can look it up. But also the polarization self-rotation, what it basically means that if the light, if the two different components of light as it goes in there, they interact differently with the given atom. And that would also change, as we have seen in this case, that the presence of field changes the energy level. So the presence of these circular beams can change the energy level, very tiny, very small amount. And that can in turn affect the polarization. So that change in the in the atomic state would affect back on the light. And therefore, as a result, there will be a sort of rotation. So as the elliptical beam passes through, it would further get elliptical or not. And now if you apply a little weak perturbing field, like it's a very noisy, weak field in X direction. It's polarized in X direction. The strong field shown by the red line is polarized in Y direction with a little amount of X so that it's elliptical. If you apply the weak field, as it goes, the light goes through, the component of the elliptical, because the beam is elliptical, it has a component along X-axis. Due to further rotation, the X-axis component would increase or decrease, and their phase may or may not be in relation to this one. So if you meet a condition in which the phase of the component of the strong field is opposite to the weak field. The weak field would be cancelled out. They would not have any weak field, any field in the X component. Everything that goes out is kind of very clean. And this is, well, this is so far all classical because the field, we're talking about fields and everything. And it's a part that plays a major role in quantum system. Here is an example. Um, so this part is a quadrature. So x1 and x2. It's related to the real and imaginary component of electric field. It can be represented as these notations, A and A dagger. So uh, these are some sort of operator for like describing a single photon. This is actually the picture of a quantum picture of photons. So otherwise, we know photons are like electric field, but the the electric field does not describe their particle nature. And to capture that, we need to use these kind of notations. So that's the kind of big role here. So just based on what I described here, if you're because these quadrature x1 and x2 is the phase and the amplitude. So if you plot and look at how the phase and the phase diagram of the coherent beam is. So coherent beam is a laser source, for example. So just a laser is called coherent source. It has phase in one kind of orientation and it's all aligned. So if you look at a laser beam on a photodiode or any detector, it will give you some power. But then over time, you will see there is some noise. And that noise is not because of the noise in the detection or electronic. We're talking about none of those. Let's say we are way past over that. But there is still some noise, and that's coming because of individual photons. The photons are arriving at some random time. So as they arrive, they would create some signal, and sometimes there'll be multiple photons, sometimes only few. So that creates a kind of a distribution in your apparent intensity pattern. So average power may look okay, but there will be some fluctuation. And if you look at the fluctuation variances, so the circle represents the variance in fluctuation. So if you measure across delta x and delta y, they're going to be the same. And this delta x, delta y, or delta x1 and x2 obeys uncertainty, Heisenberg uncertainty. So it's in some scale, therefore it's 1/4. H bar and all those things are taken into account in these equations. So as based on the polarization rotation, what happens when the power is high? So on this scale, you go operators of light to the electric field. Okay, so somebody is asking why operator is applied to the electric field. Okay, so these operators are they describe the electric field or they describe the photon. So when you're describing the spin squeezing, these photons are this is the way you would describe them. So that's just the fundamental of it. All right, so when you look at the delta x, the spread in along x-axis and the spread along y-axis, they are in this case because it looks it's circular, and that's the case with any coherent state, meaning a laser beam. So it would be circular. So both of those are going to be delta x1 is going to be 1/2, delta x2 is going to be 1/2, and then it'll be, this is also called like minimum uncertainty condition. But because of the rotation, the part which has higher, the part which is further away has higher uh, power in some sense, and due to the non-linearity, it kind of stretches further. And then the part that has lower power in the lower side stretches, stays inward. So that forms sort of like elliptical shape. So in this elliptical shape, you can see there is a elongation along this axis, whereas it is squeezed along this axis. So now you have created a squeezing, and shown on this picture. So this is the coherent state just with the normal laser, and the noise of these quadratures is going to look like this. This is circularly distributed. So okay, there's a question. Uh, does these operator have physical means to apply to electrical field or operator? Yeah, so these operators apply on quantum state, and they're called raising and lowering operator. So one would increase a photon number in the system, and the other one would reduce the photon number. That's what is used for quantization of photons, or yeah, the photon. Are they equal shapes? Yeah, so in the coherent case, they are equal in shape. But if you have a spin, product is constant. Okay. Yes. And when you have this squeezing, you will see that the noise at certain phase condition is much, much lower than the 1/2. And this is what is kind of used as a benefit for the quantum spin squeezing based sensing. So here is a term that is used, the weak field, as vacuum fluctuation. But I think it's going to take a bit longer, but vacuum fluctuations are kind of sounds very crazy, but these are real things, and they are the source of some noise. But then using the spin squeezing technique, we can minimize that and use for our kind of advantages. And such techniques are used in LIGO experiments. So it's not a remote, or it's not just a theoretical thing, but it is practical. And it's not just in LIGO, but multiple experiments have demonstrated that this kind of technique is used, and they reduce the noise level to much, much better level. One question. Okay, so the question is, can one shift squeezing in time axis? I mean, like area at one time epoch is smaller at cost of larger at one other time epoch? Just wondering. Uh, so hmm, no, it's the quadrature. It's in which has no time part in it. So it's already it's already like average effect. Coherence state. Physical example of coherence state. So coherence state in light, or is it in like just the atomic system? So in atomic system, you have two-level system in which you can create a coherence between the two, so that forms a kind of a kind of superposition. But in light, laser is a coherent state. That's where that's kind of a perfect example of that. Okay, so with this, I've come to the end of this part of the lecture, and just to summarize that we went through some issues with the classical sensing. Oh, sorry, there's a typo. And then we learned about the quantum sensing for like standard system, and walked through some examples and real world applications. Uh, we went through the basics of sensing criteria and sensing mechanism, and then discussed some types of quantum sensing. So yeah, if you have questions, please type in here, or I think this is a time that we will take a break, and we'll start afterwards. So I know I took longer in this talk, but my next talk is more on the kind of example based. So I think should work out. Okay.
Okay, sir. This was really very nice uh, talk, actually, with more conceptual learning as compared to the mathematical ones. So I'm really curious to the next session. So we'll meet again in maybe 5 minutes or so.
Okay. Yeah.
Okay. Yeah. Thank you.
See you.